All right, good day, students. We have one last thing to learn that requires mathematics, and that's the ideal gas law. So we've talked about Boyle's law, we've talked about Charles' law, we've talked about the combined gas law, which brings Boyle's law and Charles' law together, and the last thing that we're going to learn about in this unit mathematically is the ideal gas law. Our formula for the ideal gas law is PV equals nRT. So to kind of go through it, here's our formula, PV equals nRT. We know what most of these variables are, we just maybe haven't seen them for a while. So to jump right in, we have P, which is our pressure. Our pressure has to be in either atmospheres or kilopascal, and we'll get to that when we get down to the constant. But if your pressure is not in one of those two, you're going to have to convert it to that. Just like your volume, which is V, it has to be converted to liters. It has to be in liters so you can get there. N is a new one that we haven't seen for maybe a while. Maybe we've seen it, maybe we haven't, but it's been a while. N is moles. And so moles is exactly what you remember from moles in first semester. All right, moles is what we're talking about. So at some point, we might sometimes be at grams. So if we start at grams, to get to moles, we're going to have to multiply by the molar mass. All right? And sometimes, other situations, we might be at moles and we need to get to grams. And to do that, we divide by the molar mass. So that's kind of something that we need to key in for this one right here, because that's a little bit different because sometimes you have to do multiple steps. R is our gas constant, and this is the reason we have to use that. And I could put the labels on here, but they just tend to be pretty cumbersome. So we have if your pressure is in atmospheres. So if your pressure is in atmospheres, we use this one. If our pressure is in kilopascal, change the color there. If our pressure is in kilopascal, this pressure, we're going to use this one. All right. And last but not least, we have temperature, and it must be in Kelvin for us to use. So pretty simple, PV equals nRT. We might have to do some converting from moles to grams or grams to moles. So let's just take a look at an example problem and see what we got here. So our first example problem says a sample of hydrogen gas has a volume of 8.68. So there's our V. 8.56 liters, and a temperature of 0.0 degrees C, and a pressure of 1.5 atm. Cool. And it says we're supposed to find the moles of H2, and then we're supposed to calculate grams after that. So, as we go through, our pressure is 1.5 atm. So it's atm, so our gas constant that we're going to use is that 0.0821, but we'll keep rolling. V, our volume, is 8.56 liters, so that one is okay. In our moles, this is what we're finding in this case, so that's my question mark. R, my gas constant, again, it goes back to the pressure. Since my pressure is in atm, I'm going to use 0.0821. And then my T, my temperature, it's in Kelvin, or it's in Celsius right now, and we need to take it to Kelvin. Remember, that's what we have to do every single time. So we're going to add 273.15, which gives us, shockingly enough, 273.15. All right? Everybody with me so far? Cool. So now we're just going to plug this in. Here's our formula. PV equals nRT. And if we want to right up front, we can just go ahead and solve for n by isolating n. And to isolate n, if we divide each side by RT, that'll get n by itself. So n is going to be equal to P times V over RT. You can rearrange it now, you can rearrange it later. It really doesn't matter. Okay, so let's go ahead and plug in. We've got 1.5 times 8.56, double checked I've done my numbers correctly, over our gas constant, which is that 0.0821, and then times 273.15. Remember, when we type this in our calculator, we want to take 1.5 times 8.56 divided by 0.0821 and divided by 273.15. So our calculator does not get confused when we type that in. So let's throw that in our calculator. And our answer comes out to be 0.5726 or 255, and then it keeps on going. If we look at our sig figs, we have 2 in all of those, so our answer is going to be 0.57. And remember, this is moles of H2. That's what we were looking for initially. Finding moles, right? So we found moles. That's our first step. The second step says to go ahead and take that to grams. So I'm going to scroll down just a little bit here and squeeze this in. We know we have 0.57 moles of H2. And we've got to get to grams. So to do that, we multiply by the molar mass of H2. And to find the molar mass, remember we take 2 times the atomic mass of hydrogen, which is 1.00794. So we got 1.00794 times 2. That's going to give us 2.02 if we're rounding to the nearest hundredth. And now we multiply that times our 0.57, and there's our answer, 1.1 grams of H2. Take a second to make sure that makes sense. If we go back through that, we used the 0.0821 because we have atmospheres there. Plug it in. Don't forget to take our temperature to Kelvin. Plug it in. We find moles. And then from moles, we went from moles to grams. Okay? Hopefully that makes sense to you. Let's try one more. This one is where we're going to solve for temperature. If we read through it, and we're actually going to start with grams, so we got to do that math too. So we have grams here, which we can get to moles. 450,000 grams, we can get to moles from there. So I'm going to put an N above that. We have a volume of 2,700,000 liters. We have a pressure of 1 atm, and we're supposed to find our temperature in Kelvin, and then we're going to take it to degrees C. Okay? So if we plug in what we know here, we know we have a pressure of 1 atm. We have a volume of 2,700,000. We are talking about a weather balloon, so it's quite large. Our N is where we're going to have to do just a little bit of work. We have 450,000 grams, but that's grams of helium, and we're not at moles, so we need to get 2 moles. And we do that by dividing by the molar mass. So we'll put 1 mole of helium on top. We'll put the molar mass of helium on bottom, and that's 4.003. Remember that came from our periodic table. All right. So let's go ahead and find these moles here. 450,000 divided by 4.003. Oh, this is a fun number. We've got 112415.69. We'll stop there because that's a lot. That's our moles of helium. Our R, what R are we going to use? We have ATM, so we're going to use 0.0821. And then our temperature, in this case, is our question mark. So going back to our formula, slide this over just a little bit. We've got PV equals nRT. And if we're solving for T, again, by isolating it, we divide each side by nR. And that will give us T is equal to PV over nR. That kind of solves our problem for us, so we don't have to do all that arranging later. So we have 1 atmosphere is pressure. We have 2,700,000 liters over our moles, which is that big number 112415.69, and then times our 0.0821. which is our gas constant. I got a little rough right there. Hopefully you guys can see that. Whoa, I erased a lot. All right, 0.0821. And so we plug that in. We're going to take 2,700,000 times 1 divided by our 112,415 divided by our 0.0821. Alright, we finished typing that in. Our temperature in Kelvin, remember this gives it to us in Kelvin. When we find T in any of these problems, it's always going to be in Kelvin. So that gives us 292.545. If we go to sig figs, we have 1, 2, 1, 2. So we're going to say 290 Kelvin. That's part 1. Oops, lost it. So we've got 290 Kelvin. And then our second step, or our next step, is to take that 292 and subtract 545, subtract 273.15, because that'll get us to Celsius. And our answer there with 2 sig figs is 19 degrees Celsius, just a little less than room temperature if we're trying to keep track. All right, I hope that works for you. Thanks. See you next time.